This is looking at two parts, but they're the same. Limits involving infinity. So what that means is we have a limit as x goes to positive or negative infinity. But if you think about it, all functions, if they're continuous, what happens on their end behavior? They either go up or down or go horizontally somewhere. Now, what's an asymptote? Which means, yes, that's what it means. But what does it mean? It means it's a value that is, okay, as you said, it's unattainable, or it's a value that makes the function undefined. So we have two types. Actually, we have three types. Horizontal asymptotes, vertical asymptotes, oblique asymptotes. So the difference between these two, these are the limits involving infinity. What these do are as x approaches a value, the limit goes to positive or negative infinity. See, so this is as x goes to infinity, goes to a value. This one is x goes to a value, the answer goes to infinity. That's what's happening there. Can you think of any algebraic functions where this is obvious? One over x. What is the graph of one over x? It's supposed to be symmetric, but it's not. It's my horrible drawing. So these are my. What value x can we not use? What can x not equal? Zero. It's on the bottom. It can't be zero. So that's what we're going to look at first. What happens as x approaches zero to our function 1 over x? But where does it go? Actually, it's just the opposite. As it gets closer to zero, it gets bigger, bigger, bigger. You know why? Let's look at the numbers between 0 and 1. We have 1, 2, we have 4. So we have 1/4, 2/4, 3/4. So out of these three numbers, if I plug it in here, which one has a bigger answer? No. That's what everybody thinks. But let's look at this. So let's look at the first one. 1 over 1/4. it's 1/1. Flip the bottom, we get 4. 1/1/2. Take the top, flip the bottom. 3/4. 1/3/4. 1/1 times flip of the bottom, which is 1 1/4. So the bigger x becomes on the bottom, the smaller the 1/, that number becomes. Think about it. 1/10, 1/100, 1/1000. The bigger the bottom number gets, the smaller it becomes. So as we get closer to 0, the graph goes to where? Infinity. Conversely, the bigger it goes, the smaller it gets. So this one goes to where? As it goes to infinity, this graph gets lower and lower and lower. It's approaching 0. So the limit as x approaches infinity of 1/x is 0. The limit as x approaches 0 of 1/x, it goes to infinity. I know. It's just the opposite. But looking at the picture, we have to be more reserved about stating this. Why? Because as I approach 0 from both directions, are they giving me the same answer? No. As I approach 0 from the right, it goes to infinity. As I approach 0 from the left, it goes to negative infinity. Likewise, as x goes to positive infinity, it goes to 0. The limit as x goes to negative infinity, it goes to 0. This is what this section is all about. So let's look at the definition. As x approaches infinity. The limit as x approaches infinity. Because we have two infinities. We have a positive and a negative. So as the limit as x approaches infinity of some function equals some value L. Using the epsilon delta, because now we're dependent on which side we're looking at. For every epsilon greater than 0, there exists and m such that. So I was going to show you. I'll show you. Instead of writing the word for every, from the way we do with math writing, we'll say for every epsilon greater than 0, there exists an m such that. This is a shorthand for it. For all x's in the domain of f, we get f of x minus L is less than epsilon when x is positive, greater than some value m. This is going to infinity. For the first example. And the other side, this is for x going to positive infinity. We have to define this. The limit as x goes to negative infinity we have the limit as x approaches negative infinity of some function equals some limit. Then for every epsilon greater than 0, there exists an n such that for every x in the domain of the function, we have absolute value of f of x minus L is less than epsilon when x is less than n. Think about this. Why is it as x goes to infinity, negative infinity, x has to be less than some n? Because where is x going? Negative infinity. So whatever n is, we want to go further to the left. Conversely, if we're going to positive infinity, whatever m you give me, I want to go further to, I'm going to infinity. What's that? Yeah. M is greater than. It is an n. No. No, but it doesn't have to be the same values because if we have an m here and we have an n here. Because I want to go further that way. They can be the same number. They can both be 0, but I still want to go the respective distances. All right, let's look at the examples. The properties still exist. There's like the constant function. If I have a constant function and I go to infinity, what's the limit? It's the same constant function. Because remember, a constant function looks like this. If I'm going to negative infinity, it's still going to be that value. So the limit of a constant function as x goes to positive and negative infinity, it's still going to be that constant function. Likewise, the limit of what we just talked about as x goes to positive or negative infinity is still going to be zero, no matter which way you go. Some things are constant. Example 1. Show that the limit as x approaches infinity of 1 over x is equal to 0, and the limit as x approaches negative infinity of 1 over x is equal to 0. You have to use the epsilon delta proofs here. That's what it's asking you to find. Show using m and n. So let's look at the first one. How are we going to set that one up? F of x minus L is less than epsilon when x is what? Greater than m. And this other one's going to be the opposite of that. It's going to be f of x minus L is less than epsilon when x is less than n. So let's plug in our values. What is f of x? Limit of f of x as x approaches c equals L. Remember, this is our formula for limits. So what is my f of x? 1 over x. Minus L. What's my L? 0. Is less than epsilon when x is bigger than some value m. Working this out, we get absolute value of 1 over x is less than epsilon when x is bigger than m. So what does that show us? What does that tell us? What is their relationship? Remember, we used to have delta on this side. So what we're going to do, we want to compare m and epsilon. Can we do that? Not the way we have it this way. Because we have x over here. This is 1 over x. What do we have to do? Flip them. Because we have 1 over x here. This is epsilon over 1. So if we get x here, x over 1, this is going to be greater than 1 over epsilon. Epsilon is greater than 0, remember? So this is going to be a positive number. If this has to be bigger than it, then it's going to be a positive number. So what does m equal? 1 over epsilon. And that's going to be true no matter what. And we do the same thing for the other side. Go ahead and work that side out. Let me freeze this. Okay, we have this. So our function is 1 over x. The limit is 0 when x is less than n. So this becomes 1 over x. But what's the difference here? I have to keep the absolute value here. Why? Because my x's are going to which direction? Negative. So if I drop the absolute value, then it has to be less than 1 over epsilon, negative 1 over epsilon. Because I'm going to the negative side when x is less than n. So since x is less than x less than, that means n is equal to negative 1 over epsilon. I know, so it's rules of algebra. That's the reason why the absolute values were important. We can get rid of them on the positive side because epsilon's always going to be positive, 1 over epsilon, or 1 over x is going to be positive. But on this side, I'm using negative values. Epsilon can't be negative. So once I've dropped the absolute values, then now epsilon becomes negative. And also be careful about the changing of the signs, other directions. All right, let's look at example 2. Oh. All of the limit laws exist. In other words, the sum rule, the product rule, the difference rule, the quotient rule, the constant multiple rule, all those exist. They're the same. So the properties, so we have 2 of them here. Find the limit as x approaches infinity of 5 plus 1 over x. And B, find the limit as x approaches negative infinity of pi radical 3 over x squared. What the instructions tell us is, or the theorem 12 tells us that the properties exist. So what's the sum property? The sum property says if I have the limit of a plus b, I can take them individually. So the limit of a constant is what? The constant. The limit of 1 over x as x goes to infinity, 0. So the limit of this one is 5. The next one, we use the rule of constant multiples. The limit as x approaches negative infinity of pi times radical 3, that's a constant, times 1/x². So pi radical 3 can come out in front as x goes to negative infinity, 1/x². The limit as x goes to infinity of this is 0. So the answer is 0. So far, so good? So that's just telling us what happens when we go to infinity. Now we're going to look at the concepts of asymptotes in a different format. This next part is limits at infinity of rational functions. Limits at infinity of rational functions. What does that mean? Well, let's look at it. What does limits at infinity mean? Limits as x goes to positive and negative infinity of rational functions. We have two functions and they're divided by each other. Let's look at example 3. Okay, basically, here's the thing. In a nutshell, whenever you have a rational function, divide each term by the largest degree variable in the denominator. And then I'll just show you a shortcut after that. So example 3. A, the limit as x goes to infinity of 5x² plus 8x minus 3 over 3x² plus 2. And B, we're going to go to the negative infinity. 11x plus 2, 2x³ minus 1. So go ahead and work those out. Like we just said, we're going to divide all the terms by their leading, by the denominator's largest exponent. Why do we do that? Why do we divide by the largest degree variable in the denominator? See if it becomes. Yes, in essence, it's trying to find which ones become zero, yes. So we're gonna divide everybody by x squared. So we got 5x² divided by x², 8x divided by x², 3 divided by x², 3x² over x², and 2 over x². So that becomes 5. Only one of these cancels, so I have 8 over x, 3 over x². Those cancel, so we have 3 and 2 over x². Yeah, I do apologize about all the writing, but I'll show you a shortcut that you don't have to worry about this anymore. Now, following the properties of the theorem 12, the properties of of limits, since this is a quotient, we can take the limit of the top and limit of the bottom. And then we can distribute and do all those separately. Let's go ahead and skip that and combine it in this next step. So the limit of 5 is what? The limit as x goes to infinity of x 8 over x, 0. The limit of 3 over x² as x goes to infinity, the limit of 3, and the limit of that one is 0. So what we see, that's our limit. That's the L that we're approaching as we go to infinity. So there's a faster way of doing this. Only look at the leading terms. Everything else, because as we notice, besides the leading term, everything else disappears. Everything else goes to 0. So get rid of anything except the leading term. And look at the variables. More so, look at their exponents. What do we notice about here? What about the exponents here? If they're the same, then it's simply the coefficients. Since these are the same, they cancel. All we have left is 5 over 3. So that's one condition. The second, if the top has a bigger exponent than the bottom, what happens? Well, let's just say we have 2x to the 5th over 3x cubed. Again, forget the rest of the equation. So you're right, we subtract them. So take 3, and there's more on top. So as x goes to infinity, what happens to this function? It goes to infinity. Because as this goes to infinity, infinity over 3 is still infinity. So that's if the top is bigger than the bottom. If the top is less than the bottom. Here we're gonna cancel, we're gonna subtract on the bottom this time. So we have 2, 3x squared. As x goes to infinity, what happens to this equation? It's what? 0. Because remember, the limit of 1 over x as x goes to infinity is 0. So if you have more x's on the bottom, it goes to 0. Therefore, if it's on top, it goes to the opposite direction. It goes to infinity. And if they're equal, it's just the coefficients. Have you seen this before? When? In algebra. These are your horizontal asymptotes. These are your horizontal asymptotes from algebra. Let's find another example real quick. So again, the horizontal asymptotes depend on where the biggest exponent is. In other words, the degree. Is the degree on the top bigger than the bottom, or vice versa? Example 4. X cubed minus 2, absolute value of x cubed plus 1. Find the horizontal asymptotes. Okay, work those out. Find the horizontal asymptotes. All right. Find the horizontal asymptotes. We have two directions to go. We have x goes to positive infinity, x goes to negative infinity. So the first one, the limit of our function as x goes to positive infinity, and the limit of our function as x goes to negative infinity. So look at the degrees. The degrees on top and bottom are both 3. So I don't need these parts. I don't need these parts. So as x goes to infinity, where does this go? Where? 1. Because since they're the same exponents, we take the coefficients. This is 1, and that's 1. It's absolute value, it's 1. How about this one, though? There's a top's going to stay negative since it's an odd exponent. The bottom will be positive. The top's going to be negative. Cube it, it'll still be negative. So those are the limits. Okay. We're gonna have to call it short today because I have to take my wife to the hospital. She has an appointment. I totally spaced it out.